Hello guys, how are you today? So today I'll be explaining the chemistry chapter 3 course revision questions. So I'm going to be explaining them all, so from question 1 until 32 if I'm not mistaken. So let us start with section 3.1, which is about ionic bonding and dot and cross diagrams. The first part, it says, identify the type of bond between the following pairs of atom. We know that if it's between a metal and a non-metal, a metal will lose an electron. It will give the electron to the non-metal, so then the non-metal gains the electron, right? So we'll have a cation and an anion, and thus we can say that this is an ionic bond. A metal and metal, very simply from its name, is a metallic bond. And then last but not least, non-metal and non-metal is definitely for sure a covalent bond. We finished from question 1, we move on to question number 2. What does it say? It says sodium chloride, NaCl, is an ionic compound and can be represented by the following crystal lattice. Define coordination number. We said that coordination number is the number of atoms surrounding an ion, or like the number of ions surrounding other ions. We can say coordination number is the number of ions surrounding an ion. Okay, so this is the definition of coordination number. And then in NaCl, let us choose, for example, this one over here. This is Na+. Let's see how many surrounding atoms it or ions it has. We first start with 1, 2, 3, 4, 5, and 6. So it has 6 surrounding ions, which means it has a coordination number of 6. Perfect. That's it for part B. We move on to question number 3. Explain how an ionic bond forms. Okay, very simply, we can state just how we explained above, is that when a metal reacts with a non-metal, the metal loses or gives its electrons to the non-metal, right? So the non-metal will gain more electrons, so that we will form an ion in the non-metal and a cation in the metal. And when they react together, there will be a strong electrostatic force of attraction, which will result in what? Which will result in an ionic bond. So if we wanted to explain this, let me just write it up here. We should say that when a metal reacts with a non-metal, it will form a cation from the metal because the, or let me say it in a different form. Let me say that the metal gives electrons to a non-metal. The metal gives electrons to a non-metal. So we can say thus forming ions, which are the anion and the cation, and then an ionic bond. Okay, so this is how we explain ionic bonding. We move on to part B. What does it say? It says CaF2 forms when calcium, a metal, reacts with fluorine, a non-metal. Which of the following represents the correct cross and dot diagram? We said when a metal reacts with a non-metal, this is an ionic bond. And when we're dealing with ions, we don't represent it like this. We represent it with the brackets, right? So CaF2, what does this mean? This means we have one Ca but 2 Fs. So definitely directly we can see that this is the correct answer. Anyways, calcium has a charge of 2+, it loses 2 valence electrons. It will give 1 valence electron here, 1 valence electron here. And just like that, we will have what? Ca, 2+ in brackets, and then F2, F- actually in brackets. Okay, so the C is the correct answer. Anyways, we'll move on to part 4, question number 4. Give the electron configuration of metal Y, knowing that it belongs to period 3. Okay, so what does this mean? This is the biggest hint. It belongs to period 3. Okay, first we keep this in mind. It belongs to period 3. Now, what does this 3 over here indicate? This means that we have 3 Y plus atoms. Now, if you go to phosphorus, you will see that it's 3-. That means it gains 3 electrons. That means these 3 electrons are not initially for phosphorus, they were gained. That means, what does this mean? This means that each of the 3Y plus gave one single electron to the phosphorus. And from this plus over here, we can determine the group. Because it has a plus charge, we will know that this is in group 1. So we know it's in group 1 and in period 3. So then, if we check on the periodic table, group 1, period 3, here we go, that's going to be sodium. So very simply, we can state that it is sodium. And how do we get the electronic configuration of sodium? It's going to be 1s2, 2s2, 2p6, and 3s1. So that's it for 3.1. We move on to 3.2, which is only 2 questions. Define metallic bonding. Well, very simply, metallic bonding is the electrostatic attraction between positive metal ions and the localized valence electrons. So, metallic bonding is the electrostatic attraction between positive metal nuclei, or you can say ions, and negative delocalized valence electrons. So that is it for question number 5. We move on to question number 6. For each pair of metals below, determine which of the two has stronger metallic bonding. Now, usually when we are comparing between metals to see which one has a stronger metallic bonding, we need to see which one has the smaller radius. The smaller radius means it is the greater metallic bonding. So between Na and K, let's see which one has a smaller radius. First of all, Na and K, they are in the same group, right? So Na in energy level has a lower energy level than K. The shielding effect of Na is lower than that of K, and the nuclear charge of Na is lower than that of K. So all of this leads for us to say that the atomic radius of Na is lower than that of K, and because it's lower or smaller, that means Na is what it is, the stronger bonding. Now, if we compared Na or Al, they are in the same period, right? So between Na and Al, how would we compare it? First of all, being in the same period, they have the same energy level and they have the same shielding effect. But however, in regards to the nuclear charge, Na has a smaller nuclear charge than Al. But if you did the electronic configuration of Na and Al, you would get here 1s2, 2s2, 2p6, and 3s1. Here you would get 1s2, 2s2, 2p6, and 3s2, and 3p1. So by looking at this, you can assume that Al is gonna be the larger atomic radius. But I forgot to mention, my bad, that we also need to pay attention to the ionic radius. So if this is the atomic radius, right? Let's focus now on the ionic radius. Na will become Na+, right? Al will become Al3+. Perfect. Now, what does this mean? This means Na+, we will remove one electron from the S. There we go. So now we took away a single electron. So the nuclear charge of Na is reacting on the the same nuclear charge of Na is reacting on a fewer amount of electrons, so it's going to pull them closer. Whereas Al3+, we're removing 3 electrons, so all of this goes bye-bye. But the same larger nuclear charge of Al3+ is acting on the same or like a lower number of electron, but this number of electron is the same as an A+. Then for sure, this having a greater nuclear charge is going to be what? It's going to have a smaller atomic radius. So that was it for question number 6. We'll move on now to 3.3, question number 7. The graph below represents the energy of 2 hydrogen atoms. Which of the following is true? If we remember from the graph, right, that at this point over here on the x-axis over here, we would have the bond length. And on the y-axis over here, if we put this in absolute value, we would have 436 kilojoules to be what? To be the value of the bond energy. Be is bond energy, Bl is bond length. Now, at this point, it is what? It is the most stable point. Okay, so these are just 3 important factors we needed to know over here. So the most stable point exists at minus 436. This is true. The most likely radius of a hydrogen atom is 0.37. This is true. Why? Because they said radius, not like distance or diameter. We know that radius is half of the distance or the diameter. So 0.74 divided by 2, this would be 0.37. So this is also correct. So I'm going to say 0.74 over 2. Then, H2 molecule forms as energy is absorbed. No, this is wrong. And they told us at the bottom of the well, the attractive and repulsive forces are balanced so that the H atoms will maintain an average internuclear distance of 0.74. This is also true. So the 3 correct answers are A, B, and D. We'll move on to question number 8. Hydrogen chloride is a compound with the chemical formula HCl. How does the bond form between hydrogen and chloride in hydrogen chloride? In hydrogen chloride, what do we have? We have 2 non-metals, and when 2 non-metals react with each other and form a bond, this is what? A covalent bond. So they both want to attain noble gas configuration. So when they react with each other, they will share a pair of electrons because it's H single bond H single bond Cl. So they will share a pair of electrons to form a single covalent bond. So H and Cl share a pair of electrons to form a single covalent bond. Now, we will move on to question part B, 8b. Which of the following represents the dot and cross diagram for the hydrogen chloride? Now, of course, because it is a covalent bond, we do not represent it by the brackets, okay? So you directly ignore anything with brackets if it's a covalent bond. Then you need to check what? You need to check. We need to make sure that on the shell that we are drawing, okay, or the cloud that we are drawing, it should be what? It should be the valence shell, meaning it should contain the valence electrons. Hydrogen, it has only 1 valence electron, so this for sure is wrong. So this leaves us the only option being this. And we can double check by saying what? By saying that, okay, hydrogen has 1 valence electron, which is this. And then chlorine has 7, so this is 1 plus 6, which is what? Which is 7. So that means A is what? A is the correct answer. We'll move on to question number 9. Draw the Lewis structure and dot and cross diagram for each of the following molecules. We start with H2. I'm going to start by drawing all of their Lewis structures first. So H2 is H, like this only. Now, PF5. First of all, we need to choose the central atom, P. And then we have 5F surrounding, 1F, 2F, 3F, 4F, 5F, right? Now, what do? We start by counting all of the groups. So phosphorus is in group 5, plus fluorine is group 7, and we have 5 fluorine, so plus 5 times 7. And there's no charge, so it's only going to be 5 plus 5 times 7. How much is that? That's going to be 40. Perfect. Now, remember to join all of the atoms by a single covalent bond. Now, how many electrons are used here? We used 5 single covalent bonds, right? So that's going to be 5 times 2, because in a single covalent bond, we have 2 electrons. So 5 times 2, that's going to be 10. So we will subtract 10 from the number of electrons. We already used 10. So we're left with 30. 30 divided by 2, to get the lone pairs, of course, we will get 15 lone pairs. Now we start by labeling by putting the lone pairs. So we have 15 lone pairs. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. Just like that, we finished with the lone pairs. Now we checked if now we need to check if each atom fulfills an octet or a duplet. So this fulfills an octet, 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 and phosphorus fulfills more than an octet. Now, how do we check if we are sure of this? We will very simply need to go to the periodic table. So I have it in front of me. You should have it in front of you. On the periodic table, you will check phosphorus. If it is in period 3 and after, then directly, khalas, we know that it is okay for phosphorus to have what? To have an extended valence shell, meaning it can have more than an octet. So that means what we drew over here is correct. Now, SEF6, same exact concept. We're going to choose the central atom, SE. Then we have F, an F over here, an F over here, an F in the middle, an F over here, an F over here, and an F in the middle. Now, what do we start by doing? We start by taking the group, right? So SE, where is SE? SE, and my periodic table is in group 6, plus fluorine being in group 7, so plus 7 times, how many fluorine do we have? We have 6. Now, we don't have any charge, so we don't need to plus or minus. So we can just keep it as it is. So 6 plus 7 times 6, that's going to be 48. Now, we join all of the atoms to the central atom by a single covalent bond. So how many electrons did we use? We used 6 times 2, which is 12. So now it's going to be 48 minus 12, which is what? Which is 36 electrons. So if you divide that by 2, you will get 18 lone pairs. Okay, so you will get 18 lone pairs. What does this mean? This means on each atom of the surrounding atoms, we should have, we should complete the 18 lone pairs. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I think I should put it here. 13, 14, 15, 16, 17, 18. So in total, how many lone pairs do we have? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18 lone pairs. So perfect, we fulfilled all of our lone pairs. Now, what do we do in this scenario? We need to check if each atom fulfills an octet. So all of the F fulfills an octet, whereas SE fulfills more than an octet. It has 12 surrounding electrons. So for sure, what do we say in this scenario? We need to check in the periodic table. SE is in period 4, if I'm not mistaken. So yeah, it's greater than period 3, so it's allowed to have an extended valence shell. So this is what this is correct. Now, COCl2. This is a very nice drawing. We need to choose a central atom. Remember, it's the least electronegative. You can find that out by doing Focklin Brish, yeah? So out of oxygen, chlorine, and carbon, carbon is the least electronegative, so it will be the central atom. Now, what do? We have an oxygen over here, let's say, chlorine over here, and a chlorine over here. Perfect. Now, what do we start with? We start with the number of each atom's group. So carbon is group 4, plus chlorine being in group 7, but we have 2 chlorines, so 7 times 2, plus oxygen being in group 6. So 4 plus 7 times 2, that's going to be what? That's going to be... Oh, and don't forget the plus 6, so 4 times 7 plus 2. 4 plus 7 times 2 plus 6 is going to be in total 24. Now what do? We link all of the atoms by a single bond to the central atom. So how many electrons did we use? We used 3 times 2, which is 6. So 24 minus 6, that means we only have 18 electrons left. So we divide that by 2, that will mean that we will be using 9 lone pairs. So we start putting on the central atom 9 lone pairs. So this is 1, 2, 3, 4, 5, 6, 7, 8, and 9 lone pairs. Now we check. This fulfills octet, this fulfills octet, this fulfills octet, this does not fill octet. And it cannot be electron deficient because it's not boron, beryllium, aluminum. It's neither of these, so it cannot be electron deficient. So that's what we need to do in this scenario. We will need to complete the octet. Now we say, logically speaking, which of the bonds out of chlorine, oxygen, is more likely to form a double bond? For sure, it's gonna be oxygen. Oxygen is more likely to form a double bond, so we will erase this lone pair and transform it into a double bond. So now, this is what our structure will look like, okay? This is COCl2 in the Lewis structure. And now last but not least, it's C2H2. So we have 2 carbon. We'll put 2 carbon right next to each other. And then we have a hydrogen over here and a hydrogen over here. So if we write the group number, it's going to be 2 times 4 plus 2 times 1. So that's going to be 10, right? Now what do? We link all of them by a single bond to each other, or to the central atom. So just like that, what did we do? We used 3 bonds, 3 single bonds. That means we used 6 electrons. So 10 minus 6, that will leave us with 4. So now that means we have only 4 electrons to use. Now, of course, we need to put them on the surrounding atoms, but in our scenario, hydrogen is our surrounding atom. And what we need to know about hydrogen is we never, ever, ever put any lone pairs on hydrogen. So that means if we were to put our lone pairs, it will be on what? It will be on carbon. So we have 4 divided by 2. That means we have 2 lone pairs. We can put a lone pair over here and another lone pair over here. And now we need to check, are they completing the octet and the duplet? This is completing the duplet, it has 2 electrons. This is completing the octet, it has 8 electrons. This is not completing the octet, and this is completing the duplet. So what do we need to do in this scenario? We will need to change the lone pairs so that this carbon is completing the octet as well. So now this is completing the octet, but this is not completing the octet. It has only 6 electrons. So what do we do in this scenario as well? We remove this and we put it as another bond. So this is the final form. Both carbons complete the octet, both hydrogens complete the duplet. So this is what it's supposed to look like. Now that was for the Lewis structure. We drew their Lewis structures. Let us now draw the dot and cross structure. For H2, it's gonna be, because they're covalent bonds, it's gonna be H here, and then dot and cross. This is what it's supposed to look like. For PF5, we have P, we said it's the central atom, so we're gonna draw it a bit big. And we have 5 fluorine atoms, so 1, 2, 3, 4, and 5 fluorine atoms. So F here, F here, F here, F here, and F here. Now we take the valence electrons of each of the atoms. So phosphorus is 3-, that means it's supposed to have that means it's in group 5. If it's in group 5, that means it's supposed to have 5 valence electrons. And phosphorus is in fluorine is in group 7. So it's supposed to have 7 valence electrons. So it's gonna be, let's say we chose the cross for fluorine. It's gonna be 1, 2, 3, 4, 5, 6, and 7. I'll put the other one over there. Here we can do it as well. 1, 2, 3, 4, 5, 6, and 7. Same thing here. So I'm just gonna copy it quickly to save time. So basically, basically all of the fluorine electrons look like this. Okay? Now, what did we say about phosphorus? Phosphorus has 5 valence electrons. So it's going to be 1, 2, 3, 4, and 5. So what we can notice over here is that phosphorus completes the octet, and it goes even further above the octet. It has 10 electrons actually. And fluorine, each of the fluorines complete the octet. So this is fine because phosphorus is in group 3 and beyond, period 3 and beyond. So it's fine for it to have an extended valence shell. That's for PF5. Let's do SE. Actually, SEF6 is the same concept. Let us do instead COCl2. We said we chose carbon as our central atom, right? And we said that it did a double bond with oxygen and single bond with chlorine. Okay, so it would be like this. It would be carbon has 4 valence electrons because it's in group 4. Oxygen has 6 because it's in group 6. And chlorine has 7 because it's in group 7. So, in my opinion, it would be better to start with the covalent electrons or the bonded electrons. We said that we have a double bond over here, so that means we have it like this. Here we have a single bond, and here we also have a single bond. Now, let us say I took the X to be the electrons of carbon. That means the dot is for oxygen and chlorine. We know that oxygen has 6 valence electrons. So this is 1, 2. That means we still have 4 left. So we can say 3, 4, 5, 6. Perfect. There's 7 valence electrons in chlorine. We already used 1, so there's 6 left. So it will be 1, 2, 3, 4, 5, 6. Same exact thing here. 1, 2, 3, 4, and 5, and 6. So as you can see, this is what it's supposed to look like. And it's the same exact concept for C2H2. Anyways, we'll move on to question number 10. What does it say? It says, during the formation of a covalent bond, the atomic orbital containing a single electron overlap, forming a molecular orbital. What did we say these molecular orbitals are? They are sigma and pi bonds. They want us to label the following to identify the type of bond from the shown orbitals overlaps in an ethene molecule. So basically, whenever you see 2 intersections, you will directly know this is pi. And when you see 1 intersection, you will directly know that this is a sigma bond. So over here, as you can see, there are 2 intersections. Perfect. 2 intersections means that it's a pi bond. And 1 intersection in the red, right? This shows us that it is what? It is a sigma bond. So very simply, the green is a pi bond because there's 2 intersections, and the red is a sigma bond because it's only 1 intersection. We move on to part B. What does it say in part B? Which of the following molecules has 2 sigma bonds and 2 pi bonds? So what I recommend in this case, how do we find this out? You need to draw the Lewis structure of each of the following. Okay, so I'm just gonna draw them directly. HTN looks like this. Okay, so I'm gonna start with HCN. We're supposed to have 2 sigma bonds and 2 pi bonds. Let's start. Over here, if it's a single bond, it's sigma. Triple bond, that means it's sigma, pi, pi. And just like that, we have 1, 2 sigma and 2 pi bonds. So HCN is definitely a possible answer. Now, C2H6. C2H6. It looks something like this. Here, they're all single bonds, meaning we have 1, 2, 3, 4, 5, 6, and 7 sigma bonds. Okay, so it has 7 sigma bonds. We definitely don't want this. Then N2, it's N triple bond, N here and here. So this is sigma pi pi. This is 1 sigma 2 pi. We don't want this either. And then H single bond, H is literally only 1 sigma, so we don't need it either. So definitely for sure, our only correct answer is HCN. We move on to question number 11. Which of the following has a Lewis structure that's an exception to the octet rule? So I'm not gonna waste any time by drawing. I'm just gonna explain whether each one is an exception or not. This is not an exception because it is, if you drew the Lewis structure, they would both be following the octet rule. Same exact thing here. Whereas for BCl3, because it is what? Because it is one of the exceptions, boron, beryllium, aluminum, it can have a deficiency in octet, right? It can have a deficiency in electrons in the central atom. So because of this, we see that it's an incomplete octet. Now, NH, if you drew the Lewis structure, of course. NH3, BF3, if you drew it, it completes the octet. SF6, it is what? It is an expanded octet. Same thing with PCl5. And I3 minus actually, and actually everything else after. So everything else after is an exception. Why? Because they all have an expanded octet. Because of this expanded octet, it's possible, of course, because they are all found after period 2 or like period 3 and beyond, you know? So that's why it's possible. And if you drew their structure, you will see that they all have extended valence shell. Now, part B, give the Lewis dot structure for carbon disulfide. So I'm just gonna draw it really quickly. I'm gonna leave all of the work for you guys. So it's carbon, sulfur here, sulfur here. You will do double bond. And then you have bond here, bond here, bond here, bond here. Okay, so this is what carbon disulfide looks like, okay? Now, silicon tetrachloride. I will also draw it. I'm gonna leave the work for you. So it's gonna be silicon tetrachloride. So Cl, 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 right? And then each of them follows the octet. Perfect. This is what it looks like. Now, the last thing is sulfuric acid. What is sulfuric acid? Sulfuric acid is H2SO4. My bad. It's H2SO4. So, we choose the smallest atom, or like the least electronegative atom, which in this scenario is not hydrogen and not oxygen. So the only case in this scenario would be sulfur, right? So it's gonna be sulfur, and then we have oxygen, 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 and then hydrogen here and hydrogen here, right? Now, after solving, you will put all of the lone pairs and you will put the double bonds as well. And it's supposed to look something like this. I'm gonna leave the solving to you because it's gonna take me like 10 years to finish everything if I was supposed to do the solving and the drawing. So that is it for question number 11. Question number 12, what does it say? Okay, so I'm gonna choose, we already did CCl4. We already did that before. And N2 and O2, we already did that. So I think I'm just gonna do H2O and NH3. H2O is what? It's oxygen being the central atom, because hydrogen can never be the central atom, okay? So it's bonded to hydrogen, right? Oxygen is group 6, hydrogen is group 1, so 2 times 1, that's gonna be 8. Minus 4 electrons, because we use 2 simple covalent bonds or 2 single covalent bonds. So that leaves us with 4 divided by 2. That means 2 lone pairs, right? So we have lone pair here and lone pair here. Why? Because we never have any lone pair on the hydrogen. So just like that, this is our structure, and we finished H2O. Now, NH3, you choose N to be the central atom because hydrogen cannot. So you have hydrogen here, hydrogen here, hydrogen here. Nitrogen is group 5 plus 3 times 1, which is 3. So that's going to be 8 minus. How many electrons did we use in the single bonds? We used 6, so that's going to be 2 divided by 2. So it's going to be 1 lone pair. We never put it on the hydrogen, so it's going to go on the nitrogen. And this is what it looks like. Okay, now ICl4 minus and I3 minus. I'm going to draw them as well. We start with ICl4 minus I, right? And then we have 4 Cls. Now, if we did the calculation, I is in group 7, plus 4 times 7, and then it's minus, right? So that means we add 1 more electron. So it's going to be 7 plus 4 times 7 plus 1. So that's going to be 36. Okay? So 36, subtract from it how many single covalent bonds we used. That's going to be 4 times 2, 8 electrons. Okay? 36 minus 8, that's going to be 28. Now, 28 divided by 2, that's 14 lone pairs. So we should distribute 14 lone pairs. That's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. It's okay for I to have what? The extra lone pairs, because it's after period 3, so it can have an extended valence shell. So we don't forget to put the minus, because why? It is an ion. That's it for ICl4 minus. Now for I3 minus, we have I, and I. So it's basically 3 times 3 times 7, because they're all in group 7, plus 1, because it's minus. So 3 times 7 plus 1, that's also gonna be 22, right? 22, subtract from it the number of electrons. So we have 2 single pairs, that's gonna be 4 electrons. 22 minus 4, that's gonna be 18. So 18 electrons divided by 2, that's going to be 9 lone pairs. So we have to have 1, 2, 3, 4, 5, 6, 7, 8, and 9. It's okay for the central atom to have an extended valence shell, because it's in it's after period 2. Okay, so that's it for question number 13. We move on to 14. Which of the following conditions are needed for coordinate bonding? Very important. What did we say? For coordinate bonding to happen, we should have one atom having a lone pair and one atom having an unfilled orbital to accept the lone pair. Which of the following have a coordinate bond? So here we have to solve and do the Lewis structure to see which is a coordinate bond, but for now it's B and D. Okay, I'm gonna write a bunch of coordinate bonds so that we can memorize them, so we can find them easily in the exam. NH4 plus, H3O plus, CO, Al2, Cl6, SO2, O3, NO2, H2SO4. These are all what? These are all coordinate bonds we need to memorize. Okay, so this is mainly the ones that we need to know, but for sure the ones that make them are NH4 plus and Al2Cl6. So we move on to question number 15. What does it say? It says NH3 reacts with BF3 to form H3NBF3. Use a dot cross diagram to draw or represent H3NBF3. Okay, so there is a coordinate bond. We need to find that. Let us draw H3N. Oops. So honestly speaking, it's gonna be a bit difficult to draw, but I would say to separate them into two, into H3N and BF3. If we did H3N, which is the same as NH3 by the way, do you remember how we used to draw NH3? It would be N, H, 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 and then there is a lone pair. This is how we used to draw NH3. Now BF3, do you remember how we used to draw it? B, and then F, 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 and then B is deficient in electrons because it's allowed to be deficient in electrons, okay? So let me just draw that up. So it's gonna be boron over here, and then it has F, F, and F. Perfect. So now, what happens? The double bond, sorry, not the double bond, the lone pair from nitrogen will go to the electron deficient boron, and this is very simply H3NBF3. Now question number 16, a dot and cross diagram shows the arrangement of the electrons in the main energy levels. Which of the following represents the dot and cross diagram for N2? We know that N2 is N, triple bond N, and then two lone pairs here. So the best thing that will describe N2 is what is C. Okay, we move down. They said which of the following represents LiCl. LiCl is what? Is an ionic compound, right? So it's Li plus, Cl minus. So definitely for sure, it's gonna be A. Why? Because in the metal, you should draw the valence shell, which does not have any electrons. So that means B is wrong and C is wrong because it's not in brackets. That means the only correct option is A. And then C, locate the dot and cross diagram that represents pH4 plus. So first of all, we get rid of this because all of the electrons are from phosphorus. That does not make sense. Second of all, phosphorus is in which group? Phosphorus is in group 5. Meaning if we did draw it, it would be phosphorus P like this. It will have 1, 2, 3, 4, 5 valence electrons, and then it would have a hydrogen over here, and hydrogen over here. And then let's say they got an H plus, right? So this is electron deficient, this is a lone pair, it will go to the electron deficient. So it's gonna be a coordinate bond, which is definitely part B. Now, question number 7. Okay, now we reach question number 17. The table below shows the values of bond energies and bond lengths for HCl, HI, and the third unknown molecule HX. They want us to use the given data to arrange an increasing order of reactivity. What did we say? We said reactivity is the best when the bond length is the longest and the bond energy is the shortest. What does this mean? This means the smallest reactivity would be for HCl because it has the smallest bond length and the greatest bond energy. Then after that comes HX because it has the intermediate, and then which of them has the highest bond length and the lowest energy? That would be what? That would be HI. So this is what it looks like, okay? So question number 18, draw the potential energy diagram of a system of two atoms as a function of their internuclear distance for H2, O2, and N2 all on the same plot, okay? So basically all we need to do is draw one plot, okay? Like this, and then we can say that H2 is what? It's H single bond H, O2 is O double bond O, and N2 is N triple bond N. So let us just say that the one in blue is hydrogen, H2, right? So the H2 bond, because it's a single bond, that means the intermolecular distance is short, not that long. It's short, and the energy required is not too much. So if you were to draw it, it would be here until here. Let's say, for example, this is hydrogen. Now, let us say the black is what? The black is N2. N2 has probably the longest bonds, okay? And will require the most energy to break because it's a triple bond. So it's not the longest bond, my bad. It has the intermediate, my bad. N2 has, because it's a triple bond, it has an intermediate bond length, right? And it needs the most amount of energy. So if we were to draw it, it would look something like this. There we go. This is N2. And then last but not least, let's say I choose green as O2. O2 probably has the longest bond, but requires not as much energy as nitrogen. So this is what our graph is supposed to look like. So that is it for question number 18. We move on to question number 19. Use principles of atomic structure, bonding, and intermediate forces to answer the following question. Draw a complete loose structure of blah blah blah. Okay, I don't want to do that. I'm just gonna draw it directly. For part A, it looks like this. C double bond, Se double bond, Se, and then you have here, 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 okay? This is what it looks like. Now, the carbon to selenium bond length in Se2 is 180 picometer. Is the carbon to sulfur bond length expected to be longer than this, shorter than this, or equal to this value? Now, honestly, this depends on selenium and sulfur. Selenium and sulfur, if you check, they are both in the same group. So as we go down the group, we will see that the energy level of selenium is greater than that of sulfur. The scaling effect, of selenium is greater than that of sulfur, and the nuclear charge of selenium is greater than that of sulfur. So we can say that the atomic radius of selenium is greater than that of sulfur. So selenium will have the longer bond length. So the carbon to sulfur bond will have a shorter bond length. Okay, we'll move on to question number 20. Which of the following diatomic species has the largest bond dissociation energy? Bond dissociation energy is the energy needed to break the bonds. Okay, so in order to find the largest bond dissociation energy, we will need to draw and we will need to see which of them has the most bonds, okay? So we start with H2, it's H, single bond, H. Cl2, Cl, single bond Cl, and don't forget the lone pairs. Then we have N2, N, triple bond N, lone pairs, O2, O, double bond O, and then F2, so F, single bond F, and it's gonna be 1, 2, 3, 4, 5, 6. So definitely the largest bond dissociation energy will be the energy needed to break the most amount of bonds. Basically, you choose the one with the most amount of bonds, which in this case is N2. That means C is the correct answer. Now, which of the following has a bond order of 2? The only correct option would be O2, so the correct answer is D. Finally, we reached the resonance and formal charges. Below are possible Lewis structure of the sulfate ion. Use the formal charges to predict the most probable structure. Now, my first priority in this, honestly speaking, is to take the central atom and ensure that the charge of the central atom, the formal charge, is 0. Again, how do we find the formal charge? We take the group number and subtract it by the number of surrounding electrons. So group number of sulfur is 6 minus surrounding electrons. You cut these in half, so you don't take it as the full 8 electrons. It will be divided by 2. So it's gonna be 4. 6 minus 4, that's gonna be 2. That's gonna be plus 2, and we cannot have it to be plus 2. We need to ensure that it is 0. Over here, it's gonna be 6 minus 5, which is plus 1. We don't want that. Here, it's what? Here, it's 6 minus 6, which is perfect. This is the one we need. That means C is the most probable and perfect option. We move on to question number 22. What does it say in 22? Show all the resonance structures for NO2 minus and O3. So let us draw an O2 minus. We start with N and we have 2 oxygens, right? Now, N is in which group? N is in group 5 plus oxygen being in group 6. And because it's minus, we will add 1 electron. So it's gonna be what? It's gonna be 5 plus 2 times 6 plus 1. So that's gonna be 18. Now, you give single bond to each, so that's minus 2 times 2, which is 4. So that's gonna leave us with 14 divided by 2. That's gonna be 7 lone pairs. So we have 1, 2, 3, 4, 5, 6, and then 7 over here. Now this completes octet, this completes octet. The central atom does not complete octet. So I could take from here and I could make it a double bond. It works like this, or I could do it like this, or I could have another form which is like this. So I just switch the place of the double bond. So this is the definition of a resonating structure, in that the double bond can switch. So this is the definition of resonating structure, or the, resonance structure. What did I click? My bad. Okay. We'll move on now to O3. O. Okay? Now this is gonna be 3 times 6. That's gonna be 18. We subtract from it 4 because we used 2 single bonds. That's gonna be 14 divided by 2. That's supposed to be 7 lone pairs, right? So 7 lone pairs mean we have 1, 2, 3, 4, 5, 6, and 7. So what do we need to do? Again, same process. It could either be like this, or it could be like this. So if the double bond can change places, then it is what? It's a resonance structure. Now we finished 22, we move on to 23. Calculate the formal charges of Cl and O atoms in the following Lewis structure. Number 23 grid. Calculate the formal charges of Cl and O atoms in the following Lewis structure. Of course, how do we calculate the formal charges? You need to take the group number. For example, Cl is in group 7, and we will subtract from it the surrounding electrons. So it has 1, 2, 3, 4, 5, 6, and 7 electrons. So that's gonna be 0. And then for oxygen, it's gonna be what? It's gonna be the group number, which is 6 minus the surrounding electrons. So 1, 2, 3, 4, 5, 6, and 7. So that's gonna be 6 minus 7, which is minus 1. That is the formal charges. Now we move on to section 3.5, which I believe... Oh, okay, perfect. We don't have too much. Now section 3.5 is all about solving. They said a sample containing 0.78 grams of potassium reacts with enough oxygen to produce 1.1 grams of a single product A. What's the empirical formula of A? So, potassium reacts with enough oxygen to produce 1.1 gram of a single product A. Okay? So 0.78 grams of potassium reacts with whatever mass of oxygen to produce 1.1 grams of this unknown substance. So how many grams of oxygen did we use? We used 1.1 minus 0.78, which is what? Which is 0.32 grams. Perfect. Now we need to find the number of moles by doing mass over molar mass. So 0.78 over 39, 0.32 over 16. This is gonna be 0.02 moles, 0.02 moles. Now what do we need to do in this scenario? We need to find the simplest ratio. How do we find the simplest ratio? You divide by the smallest number. In this case, because they're the same number, it's gonna be a simplest ratio of 1 to 1. So what does this mean? This means that it's gonna be KO, potassium oxide. That means the empirical formula is KO. You have 1 potassium, 1 oxygen. Perfect. Question number 25. The composition by mass of compound Z of general formula, or of general molecular formula CXHYOZ is 40% carbon, 6.7% hydrogen, and 53.3% oxygen. They want us to find the empirical formula of compound Z. How do we find this? Let us assume that the total mass of the compound is 100. If that's the scenario, right, because it's carbon, I think I need to zoom in a bit more, right? I'm just going to memorize the values because I need the blank space. We have what? Carbon, hydrogen, and oxygen, right? Carbon, if I'm not mistaken, it was 40%. Hydrogen was 6.7%, and oxygen was 53.3%. Now, if you add them all in total, it's going to give you a total of 100, and this is what? The simplest formula. I'm going to call it S. So now what do we need to do? We need to find the number of moles. So we'll divide everything. It's going to be 40 divided by 12, 6.7 divided by 1, 53.3 divided by 16. And what will we get as the number of moles? We will get 3.33, 6.7, and here we will also get 3.33. So now we need the simplest ratio, meaning we will divide everything by the smallest number. So divide everything by 3.33. And we will get an approximate ratio of 1 to 1. So the ratio is 1 to 1. That means the simplest is going to be CH2O. Perfect. Okay. Now we have what? We have the empirical formula, which is CH2O. The relative molecular mass of compound Z is found to be 180. Deduce the molecular formula. So we know that it is CH2O, meaning the empirical mass is going to be 12 plus 2 plus 16, which is 30. So if the molecular mass is 180, it's going to be 180 divided by 30, which will give us a ratio of 6. So this ratio 6, we're going to multiply it by the empirical formula. So it's going to be C6H12O6, which is what? Which is glucose. And that is it for question number 25. We move on to question number 26. What does it say? It says a compound contains only C, H, N, and O. Combustion of this, okay, produces 0.213 grams of CO2 and 0.0310 grams of H2O. In another experiment, okay, perfect. They want us to find the empirical formula of the compound. So look what we're gonna need to do. I'm gonna zoom in a bit so I can take as much space as possible. The first thing we will need to do is we will need to find the number of moles of carbon, hydrogen, and nitrogen. We start with the number of moles of carbon. Number of moles of carbon is the same as the number of moles of CO2. Why? Because we have one carbon here and one carbon here. So that's going to be the mass, which is 0.213, over the molar mass of CO2, which is 44, so it's going to be 4.84 times 10 to the power of minus 3 mole. Now, after we found the number of mole of carbon, we move on to the number of mole of hydrogen. The number of mole of hydrogen is the same as 2 times the number of mole of H2O. Why is it 2 times? Because we have one hydrogen here, but we have 2 hydrogens here. So to compensate this 2, we will need to multiply the whole number of moles by 2, right? So it's going to be 2 times the mass, which is 0.0310, divided by the molar mass of water, which is 18, which will give us the answer to be 3.44 times 10 to the power of minus 3 mole. Now, I don't know if I can go up. I don't think I can go up. Oops, that's fine. Let's ignore that. Okay, I don't want to waste my work, so I'm just going to leave it like this. And so, anyways, if you want, just like keep this in mind, write it down, have the number of moles of carbon, of hydrogen written down, just so I can get rid of this now. Okay, so we have the number of moles of carbon, the number of moles of hydrogen. What's left is to find the number of moles of nitrogen and oxygen. First of all, let's find the number of moles of nitrogen. It's the same as the number of moles of NH3 because one nitrogen, one N. Okay, so it's going to be the mass, which is 0.0230 over the molar mass of NH3, which is 17. So that's going to be 1.35 times 10. Oops, I think I collided them. So that's going to be 1.35 times 10 to the power of minus 3 mole. Perfect. Now that we have the number of mole of carbon, hydrogen, and oxygen, we'll be able to find what? We will be able to find their relative masses. So we need to find the mass of carbon, the mass of hydrogen, and the mass of nitrogen. Very simply, it will be the number of moles times the molar mass. So it's going to be 4.84 times 10 to the power of minus 3 times 12. Then here it's going to be 3.44 times 10 to the power of minus 3 times 1. Okay? And here it's going to be 1.35 times 10 to the power of minus 3 times 14. Right? And then we will get what? We will get the respective masses. So this is going to be 0.0581 grams. This is going to be the same, which is 3.44 times 10 to the power of minus 3 grams. And then this is going to be what? This is going to be 0.0189 grams. Now that we have all of the masses saved, what can we do now? We can find their respective percentages, right? So now that we have the masses of all of the respective ones, we can change them into percentage. So we'll take percentage of carbon, percentage of hydrogen, and percentage of nitrogen. This is gonna be 0.0581 over the total mass, which is 0.1557 times 100, which will give me a percentage of 37%. Of course, you need to put it to the correct significant figures, which in this case is 3. Then for hydrogen, it's 3.44 times 10 to the power of minus 3 over 0.1557 times 100. So that's gonna be 2.19%. And then for nitrogen, it's gonna be 0.0189 over 0.1557 times 100, so that's gonna be 18.4%. Now we have all of the percentages, and remember, in any compound, all percentages add up to 100. So how do we find the percent of oxygen? Percent of oxygen is equal to 100 minus, what was the first percentage? 37.0 minus 2.19 minus, because we put it in brackets, you put it plus 18.4%. So in total, it's gonna be 100 minus, open brackets, 37.0 plus 2.19 plus 18.4, and we will get an answer of 42.4%. Okay, so this is the percent of oxygen. Now we need to find the simplest ratio, so we will need to separate them like this. So what do we have now? We have carbon, hydrogen, oxygen, and nitrogen, right? So carbon, we said we will take the percentage, which is 37.0. Hydrogen, we will take the percentage to be 2.19. Oxygen, we took it to be 42.4. And nitrogen, we took it to be 18.4. Actually, if we do go up, I think they want it in the form of CH and then O. Okay, so we will put it, we'll just change the order. CHNO. So now it's what? It's 37, 2.19, 18.4, and 42.4. Perfect. Now we're going to divide each of these by what? By their molar masses, because we're going to consider the total mass to be 100. So we'll divide by the molar mass, 12, 1, 14, 16, and we will get what we will get moles. So this is going to be 3.08, 2.19, 1.31, and 2.65. And just by this, we'll be able to find what? We will be able to find the number of moles. Now we divide everything by the simplest ratio. So divide by 1.31, 1.31, 1.31, and 1.31. And we will have what? We will have 2.35. 1.67, 1, and then we will have 2 over here. Now, of course, this is not in simplest ratio. So how do we get it to the simplest ratio? Well, actually, very simply, if you did 3.08 over 1.31, you would get 2.35, right? So basically, what we'll need to be doing in this scenario is we're going to keep on multiplying by multiples. So we start by 1. It will not give me a full number, so I don't take 1. I will do 2.35 times 2. It will give me 4.7, not a whole number. I don't want it, so I do times 3. 2.35 times 3. I will get 7.05, which is the closest possible value you will get to a whole number. So what we need to do now is we need to multiply the whole thing by 3. So let's say we multiplied this by 3 and we got it to be 7. Because if you rounded it, it's 7. Then 1.67 multiplied by 3, you will get 5.01, which is approximately 5. 1 times 3 is 3, and 2 times 3 is 6. So the simplest possible ratio would be C7, H5, and 3O6. Now we move on to 27 grid. A hydrocarbon sample with a mass of 3 grams underwent combustion, producing 5.5 grams of carbon dioxide. If all the carbon initially present in the compound was converted to carbon dioxide, what is the percent of carbon by mass in the hydrocarbon sample? Yeah. Well, very simply, they want us to find the mass of carbon present in the hydrocarbon. In order to do that, we will need to find the number of moles of carbon. We can find the number of moles of carbon knowing it's the same as the number of moles of carbon dioxide. So it's going to be 5.5 grams divided by the total mass the molar mass of carbon dioxide, which is 44, so this will give us 0.125 moles. Now that we have the number of moles, we will be able to find the mass of carbon. It's gonna be the number of moles multiplied by the molar mass to give us 1.5 grams. Now they want the percent, so it's gonna be 1.5 over 3.0 times 100, so that's gonna be 50%. Okay? We'll move on to 28, deduce the chemical formula of each of the following. So this is pretty easy. Oxygen difluoride, OF2, magnesium oxide, MgO, sulfur hexachloride, sulfur is S, chloride is Cl, hexamine 6, so SCl6, ammonium nitrate. So ammonium itself is NH4, and nitrate is NO3, so NH4, NO3. Now, magnesium trichloride. What does this mean? Sorry, not magnesium. Manganese, my bad. Manganese trichloride. What does the tri represent? It represents the charge. So it's gonna be Mn3 plus Cl minus. Do the crisscross method. MnCl3. So over here it's MnCl3. Now, lithium hydrogen carbonate. First of all, we know lithium is Li plus, hydrogen carbonate is HCO3 minus. So we do the crisscross, we will get LiHCO3. Now, calcium hydroxide, it's Ca2 plus, OH minus. You do the crisscross method, you will get CaOH2. So the product over here is what is CaOH2. That's it for this question. Now we'll move on, my bad. We'll move on to question number 29. They want us to name the compounds. So very simply over here, this is gonna be what? This is gonna be sodium sulfate. Sodium, because we have sodium, and then sulfate. This is gonna be aluminum bromide. Now, why do we name it like this? Because these are ionic bonds, ionic compounds. They are not covalent. So we don't use tri, di, penta, hexa. We don't use these. No, we just state element, because they are ionic. AlBr is also okay. So because this is ionic, this is gonna be what? This is gonna be aluminium bromide. Now, this is not ionic. This is non-metal and non-metal. So it's a covalent bond. Now we can start using di and the prefixes and whatever. So it's gonna be diphosphorus pentoxide. Okay? Di because we have 2, pent because we have 5. Now I'm just gonna clear those out. NO is nitrogen monoxide. So nitrogen monoxide. CaCO3 is calcium carbonate. CuCl2 is okay, because this is ionic, it's calcium carbonate. This is also ionic, so it's gonna be what? It's gonna be copper chloride. Now, the only catch here is because copper is a transition metal, we will need to put the oxidation number. So copper in this scenario, if you split them, it's gonna be Cu2 plus and Cl minus. So what's the oxidation number 2? So it's gonna be copper 2 chloride. Perfect. And now here Fe2O3, this is also ionic. So it's gonna be iron oxide, but we check the oxidation number. It's iron 3 plus, Fe3 plus O2 minus. So it's gonna be iron trioxide, or like iron 3 oxide. Okay, so that's it for question 29. We move on to 30. What does it say? It says predict the formula of the ionic compound formed by the following pairs. Mg is Mg2 plus, N3 minus. If you don't know how to check them, you go to the periodic table and you start. You're gonna be like, this is plus 1, plus 2. You skip all of these, plus 3, then minus 3. Or sorry, no, these can be plus 4, minus 4. Then plus 3. Or sorry, not plus 3, minus 3. Minus 3, minus 2, minus 1, and 0. This is how you do it here. And the transition metals, usually they will give it to you. What's the oxidation number? So in this scenario, this is how you know. So I checked, okay, what did I have? I had magnesium. Magnesium is 2 plus, and I had nitrogen. Nitrogen is 3 minus. So I do it like this, and I check what I have. So what's it gonna be? It's gonna be Mg2 plus, N3 minus. Do the crisscross. Mg3, N2. Al and O, aluminium, 3 plus oxygen, 2 minus, do crisscross, Al2O, 3. Li and O, Li plus, O2 minus, do the crisscross, you will get Li2O. Ca and F, Ca is Ca2 plus, F is F minus, do the crisscross, you will get CaF2. That is literally it for question number 30 grid. We move on to 3.6 now. It's a very easy concept now. Now they told us cobalt chloride may exist as pink or blue crystals. They wanted us to know if it's anhydrous or hydrated. How do you know if it's hydrated? If you see water in the compound, you directly know it's hydrated. If you don't see water, you know it's anhydrous. What's the name of the water molecules that are a part of the structure of COCl.6H2O? Because they are crystals, we will call this what we will call this water of crystallization. Okay? Very simply, that's it for this question. Now the last and final question. Copper 2 sulfate exists as blue crystals and blah blah blah. They gave us the molecular mass of this, right? They want us to calculate the value of X. Very simply, in order for us to calculate the value of X, we will need to find the number of moles. We first start with the molar mass of water. Molar mass of water is what is 18. This is known already. So now what do we do in this scenario? We will take the total mass of this blue crystal, okay? So 249.5, and we will subtract from it the mass of CuSO4. What's the molar mass of CuSO4? It's going to be 63.5 plus 32 plus 16 times 4. So it's going to be 249.5 minus, open bracket, 63.5 plus 32 plus 16 times 4, close brackets, and you will be left with 90. So this is the mass of water. So it's going to be 90 mass divided by the molar mass 18 will give me 5. So this is the number of moles, which in this scenario is the value of X. So that's it for this video. Thank you guys for watching. I hope you enjoyed and have a wonderful day.